Okay, so in the previous lectures, what we were discussing about was the basics of computer vision with respect to images. We saw different filters that could be used for spatial as well as frequency filters that could be used for processing those images. We also looked at the image feature extraction or texture feature extraction methods. We had looked at feature descriptors, the feature detectors like HOG and SIFT. We had looked at the concept of ransack and so on, right? So in today's class, we'll be discussing or we'll be going through an introduction to affine and projective geometry. Okay, so what is projective geometry? We'll see that first. So let's say let's say you're taking the picture, okay, of a wall. So let's say this one that you see here. Let me take my laser pointer. So let's say this is a picture of a wall, okay, a wall which is made of bricks, right? Now, as you can see, this is a picture which I have taken from the camera facing perpendicular to the plane of this wall, okay? And this is a picture which I have taken by going, let's say, nearer to one end of the wall, and then taken the camera view from one end of the wall focusing to the other end, okay? So this is in this particular view, the camera positioning, okay, or the camera view is not perpendicular to the plane of the particular wall, okay? And you can see how the same object in 3D, the same 3D object in the scene can have two different views, okay, by just changing the camera viewpoints or the camera positions, right? So here, if we look at this particular picture, what we see is just like how you see the particular wall in a 3D view. Okay, that is with the bricks, which is perfectly rectangular in shape, and with all the shape of the bricks as well as the length of all these bricks, everything, okay, appears to be the same as that which is occurring or as that we see with our human eyes in 3D, right? But when we look at this particular view, okay, or this particular viewpoint, from this particular viewpoint, what we see is that it kind of all these bricks over here, it kind of looks a little bit stretched over here, but at the same time over here it looks a little compressed, okay? And these brick lines, if you see, if you look at the borders of these bricks, okay, they are what I say, they are not exactly the lengths, okay, are not exactly preserved in this case, okay? And with respect to the lengths over here and the lengths over here, these are not preserved, right? The shape, correct, these are longer rectangles, these are shorter rectangles, and so on. So we can see that just by having these two viewpoints of the same object, you can have two different images with different lengths of the basic elements, that is basically bricks in this case, in these two images, right? So from here we'll just try to understand what is projective geometry. So what you have studied in earlier classes, okay, is regarding Euclidean geometry. So in Euclidean geometry, it is basically the Euclidean geometry includes transformations with respect to translation and rotation and so on. Okay, so for each of the geometry or for each of the space, be it Euclidean, affine, or projective, it has got some certain transformations, okay, of its own that allows certain properties of that particular space to be preserved, right? Now, in the case of projective geometry, okay, what we see is that the lengths, the angles, the shapes, etc. over here, it is not preserved. Okay, so you might have a view which looks somewhat like this. Now, just to take another example, let's say you're assuming this to be, instead of a brick wall, you're assuming this to be a cube structure, okay? So in a cube, all the faces of the cube will be having the equal lengths, right? Now if I'm taking the picture of the cube, okay, where the camera is the camera point or viewpoint is perpendicular to that of the surface of the cube or a particular face of the cube, then what we get would be kind of a square-like structure, right? You'll get a square if it is perpendicular, only if it is perpendicular. But if the viewpoint changes, okay, if I'm taking from some other viewpoint, then what happens is that it is no longer a square, right? So same case with with respect to the circles also. As the viewpoint changes and the image plane changes, a circle may be projected as a ellipse, okay? So here in this particular image, if the viewpoint was perpendicular and you have the image plane over here, what you get would be a circle. But in any other viewpoints, you see that the projections that you get would not remain a circle. It would remain, or what you get would be an ellipse, right? So here comes the concept of projective geometry. That is, in projective transformations, okay, what happens is the squares may not be always squares, or the circles may not always remain circles. If the camera viewpoint is perpendicular to that of the object's surface, then you would get the expected geometry or the shape, right? But otherwise, what happens is in all other cases, the squares and the circles, the shapes, the angles, the lengths, they are not preserved. Okay, so such transformations, okay, can be called as projective transformations where, okay, there is only one particular property that we'll see later, okay, which is the only one property which is preserved, okay, but except for that, the shapes, lengths, etc., all those are not preserved, okay. But when you've studied about Euclidean geometry, what Euclidean geometry means is that in Euclidean geometry, it is basically a translation and rotation, right? So the length of the object, the shape of the object, the angle between the lines of the object, everything is preserved when it comes to Euclidean geometry, okay. But in projective geometry, it is not. So these are some of the properties of projective geometry, okay, where the shape is not preserved, the length is not preserved, the angles, the distance, the ratio of distance, etc., all these are not preserved. So the only property that is preserved, if I just take you back to this particular two set of images, the only property which you can say is preserved in these two images, or in the case of a projective geometry, is that the lines which are straight, okay, in actual 3D view, when you're looking at the object, the lines which are straight still remain straight, okay. So that means the straightness of the lines are the only thing which is preserved, okay. Not even parallelism, even parallelism is not preserved. If you look at this, if it's a longer wall, right, this goes on like this, so it's not parallel anymore, right? So it is the fact that a straight line remains a straight line, okay, or all properties with regard to straightness of lines, like for example collinearity, etc., these are the only things which are properties which are preserved in the case of projective geometry. So this is a point that you need to remember, that straightness is the only property which is preserved in projective transformation, okay. But projective transformation, okay, it is very important when it comes to computer vision, because many algorithms in computer vision uses this projective transformation, or requires the use of this projective transformation. We'll see why, okay. So in order to understand that, let's just try to understand the Euclidean geometry. So as I said earlier, in Euclidean geometry, the angles, the basic shapes of the objects, the lengths of the objects, etc., all these are preserved with respect or when it comes to Euclidean geometry, right? Now in Euclidean geometry, what we assume is that two lines in 2D, if you're taking a 2D picture, let's say, okay, so given any two lines, it will always meet at a point is an assumption that we make. So it is based on this that we have all the different laws or properties that come under the Euclidean geometry, right? So all any two lines in 2D will meet at a point. And in the case of parallel lines, if it is parallel lines, what we do is we assume that these parallel lines will meet at a point in infinity. They will meet, but at a point in infinity is what is assumed in the case of Euclidean geometry, right? So the problem with Euclidean geometry is that when you say that the lines meet at a point in infinity or they meet at infinity, what exactly is infinity? Or how do you represent infinity? How do you denote infinity? That is not defined in Euclidean geometry or Euclidean space. Okay, and that is a limitation of Euclidean geometry. So, for example, if I take any two lines, okay, those two lines, a line can be any line can be drawn if you know at least 2 points that passes through or that lies on the line, right? So let's say the point which I'm considering is, let's say, x1, y1. Okay, the x and y coordinates in the 2D image. Okay, so I have x1, y1, and I have x2, y2, and so on, right? But when it comes to a point at infinity, okay, what are these values of x and y, or how do you represent that? That representation is not there in Euclidean geometry. Okay, but we require these points at infinity. Okay, that is the point at where in which the parallel lines meet, or the point at infinity, or the concept of infinity is required when it comes to computer vision, when you're coming to different algorithms with respect to computer vision. Okay, so because Euclidean geometry does not have such a representation, we go for projective geometry. Okay, so in projective geometry, what is different from that of Euclidean geometry or the Euclidean space is that, okay, along with the Euclidean space, you're adding a representation for infinity or for the points at infinity in the case of projective transformation, right? So when you projective transformation or projective space is nothing but the Euclidean space along with a representation for the points at infinity. Okay, so we'll be coming through the details of what exactly this means later. Okay, what you have to remember is that because in projective geometry you have a specific notation for points at infinity, it becomes easier to work with such points at infinity, which is also very essential for computer vision, right? And that is why in computer vision we go for, or the projective geometry is mostly dealt with, or it is mostly used. Okay. Now, okay, so when you are talking about, I told that there is Euclidean geometry, okay, there is affine geometry, and there is projective geometry. What each of these geometry or what these of each of these transformations include, we'll be discussing in detail later. Okay, so one thing you have to remember is, according to the Erlangen program, okay, when you are talking about a particular geometry, be it Euclidean geometry, be it affine geometry, or be it projective geometry, any of these geometries, right? When you're defining a geometry, you are not defining in terms of the objects, okay, which it represents, but only by the transformations that it allows, or the transformations which it supports. Okay, like for example, when I'm talking about Euclidean geometry, I would say that Euclidean geometry, okay, are those or it is those space in which so and so transformations, after applying so and so transformations, the basic properties of this space are still preserved. Okay, such transformations can be called as a Euclidean transformations. So when I'm talking about this geometry, right, I talk in terms of the transformations which can happen in this particular geometry, or in this particular Euclidean space. Okay, if I talk about affine geometry or affine space, I speak in terms, or I define it in terms of the transformations that it supports. For example, in Euclidean geometry, the transformations that it supports, as I said earlier, is the translation and rotation. So what translation means is, if you have a particular object, okay, if you, it's as if you are, you know, you can imagine it as if, you know, you're moving the object to another location, as such. Okay, you can assume it that way. Okay, but later we'll see that the objects, it remains the same and it remains at the same location, and instead of assuming it as objects being moved to another location, we can assume, basically just assume that the axes are changed. That's all. We'll see that later. Okay, so for now what you have to remember is that when you're talking about a particular geometry, right, we define it, or we represent it in terms of its transformations that it allows. So each and every geometry has got a set of transformations, okay, which it allows, means which it supports, means that those transformations which, when applied to that particular geometry or space, okay, still the properties of that geometry or space remains the same. Now just have a look at this particular picture. What we see is you have this Euclidean geometry, and as I said, in Euclidean geometry of space, the transformations it supports is basically translation and rotation, right? Now, if you go to a fine geometry, okay, so it has got an additional transformation. Okay, basically it's the scaling or the linear stretching transformation. Okay, along with translation and rotation, it has got this additional transformation that it supports. Okay, and if you go to projective geometry, what you see is that again the projective geometry supports all the transformations which are the affine as well as the Euclidean transformations, along with some other additional transformation, right? So what you can say is that the Euclidean transformations over here, it is a subpart of affine transformation as well as projective transformation, or I can say affine geometry or affine space, it is a subpart of projective transformation or projective geometry. Okay, but projective transformations, okay, or projective geometry, it is not a sub part of these, right? These are included within the projective geometry, which is the whole picture, okay, or fuller picture as compared to the Euclidean and affine. Okay, so as I said, there are some Euclidean transformation along with another transformation gives you a fine geometry, and a fine geometry along with another transformation gives you projective geometry. What are these transformations? We will see that later. Okay, so what you have to remember here is that Euclidean and affine geometry of space are basically a sub part of this projective transformation of projective space. Okay, so all the projective transformations, okay, it basically contains all the affine transformations as well as the Euclidean transformations. Okay, but you cannot say that all Euclidean transformations contains all projective transformations. Okay, so if you look at this particular figure, you'll get the idea of what I'm trying to say. Okay, now what you're familiar here with respect to the transformations is the Euclidean geometry, that is the translation and rotation. So we'll speak about that, and then we'll see how we can change that to the projective geometry, and then after that we'll come to the affine geometry. Okay, so this is just an example of what this means. So let's say the initial picture that we have is a square over here. Okay, so in Euclidean transformation, that is when you're doing a translation operation or a rotation operation. Okay, what happens is, let's say after a particular operation, this is how the shape looks like. The shape of the object looks like, right? So what we see here is that the basic shape of the object remains the same. Okay, the lengths are preserved over here. The angles between each of these lines are also preserved. So this is a Euclidean geometry, which we are the most familiar with, right? Then similarity geometry or similarity transformation is something that we are not looking at right now. Let me just go to affine. So in affine transformation or affine space, along with translation and rotation, okay, it also has got a transformation which is called as the scaling or linear stretching. Okay, so apart from translation and rotation, can also scale this or you can stretch this, right? So this is after a particular stretching operation, an example of how the object looks like. So this transformation is supported by the affine geometry or affine space. And when it comes to projective space, as we have already seen earlier, the shape is not preserved, the lengths are not preserved, the angles are not preserved. The only thing which is preserved is the fact that the lines are straight. That's all. Straight lines remain straight is the only thing. So parallelism is not supported in projective transformation. That is a very important point you need to remember. Okay, in projective space, the parallelism of the lines are not preserved. Okay, so before we go on to the coordinates, let me just try to uh, just summarize this 1 minute. Okay, so what we were discussing about now was in terms of 2D, right? So if you have a two-dimensional, just write it here. If you have a, let's say, two-dimensional representation in Euclidean space, right? So all points, so this is with respect to 2D space, right? So all points here, they are represented by 2 dimensions, right? And if it is a 3D space, I have it, let's say like this, I have the 3D space, right? And here all points, they are represented in 3 dimensions in the case of 3D space. So let's say if I'm representing it as x comma y, here I represent it as x comma y comma z, right? So we'll be first looking at how the representations are with respect to 2D, okay, and we'll see what the different concepts with regard to the Euclidean and projective spaces in 2D space, okay, and then we'll move on to 3D space, okay. And we also saw that in a given space or geometry, okay, so let's say you're talking about Euclidean geometry. If you apply certain transformations, okay, if you apply that and still the basic property of that particular space is not changed, okay, so then that means those transformation is supported or allowed in that particular space or geometry, okay. And we saw that in the case of Euclidean, those transformations are basically the translation and rotation operations, okay. And what we see is the shape, the angle, the length, etc. are preserved in the case of Euclidean, right? Now there are certain transformations which are allowed in certain space but not in certain other space. Like for example, in the case of affine, we saw that a shearing operation can be applied over here, right? So by shearing, what happens is you get this kind of what to say, a shape over here, right? But shearing operation or the scaling operation, linear stretching operation, all these comes together, right? So this one is not supported by the Euclidean geometry, right? So there are certain transformations which are allowed in certain space but not allowed in the others, okay. So which transformation belongs to which geometry depends upon whether it preserves the basic properties like shapes, angles, and lengths in that particular space, okay. So that's one thing you have to remember. Now another point which we discussed just before is that uh, we discussed what is Euclidean space. We said that in Euclidean space there is no representation of infinity, and that in projective space it is an enhancement or enhancement of the Euclidean space along with a representation for infinity, right? So we will see what exactly is this particular representation or notation that we use to denote infinity in terms of or in the case of projective space, okay. So in Euclidean space, right, so all the numbers or all the points that we are taking, right, it can be represented in terms of x comma y, right? So if you have a point, let's say x1 y1, another point x2 y2, where all this x1 x2 y1 y2, all these belong to real numbers, right? So all the points in Euclidean space, they can be represented by the notation x comma y, right? Now, what we do in the case of projective space is that, okay, to represent these points in projective space, we add an additional coordinate. Okay, we just add an additional coordinate, a third coordinate. Let's take it as 1 over here. So x comma y comma 1, it represents the same point, okay, which we have defined over here. It is the same point, but now this in projective space or projective geometry, we are representing it with a third coordinate. Okay, so why this is required is something which we will see later, or how this can be used for representing infinity, we'll see that later. Okay, so now you have to understand that this is a way how you represent using three different coordinates in 2D space. You use three coordinates to represent the this particular same point in the case of projective geometry or the projective space. Okay, and if you want to, so if from Euclidean space, if you want to go to projective space, you add this third component over here, you add a comma 1 in this case, right? If you want to go back from the projective geometry, if you want to go back to the Euclidean geometry, right, what you do is you simply have to divide by the third coordinate, that is, okay, so let's say in projective space the coordinate I have is x comma y comma 1. And then if I want to represent the same point in the case of Euclidean space, what I can do is x divided by the third coordinate comma y divided by the third coordinate. Okay, this would be my representation of this particular point in Euclidean space. Okay, now so these are the ways by which you represent the points, right? And x comma y is a way, or is a representation or a notation which you're already familiar with. This is a new concept that you are learning, that is in projective space you have the third coordinate over here, right? Now you have names for these coordinates, right? So this kind of representation where you're giving x comma y, right? This is called as the non-homogeneous coordinate. Okay, you call it as a non-homogeneous coordinate. And this particular representation where you have x comma y comma 1, right? This is called as the homogeneous coordinate, right? So this homogeneous coordinate is used to represent the projective space. Okay, and this non-homogeneous, it represents the Euclidean space. So remember that when we have to convert or find what is the equivalent point, okay, of this particular point which is given in projective, which is defined in projective space, if you want to find that in the Euclidean space, what we do is we just divide by the third coordinate. Okay, so this is in the case of 2D. Now, if it is 3D, if we are discussing about 3D, in the case of 3D, we know that in the Euclidean space or Euclidean geometry, you have three coordinates. It would be x comma y comma z, right? So in the projective space, how we represent that is you will have a fourth extra coordinate. So you'll have it as x comma y comma z comma. I'll just take 1 over here for this example, right? So you use 4 different coordinates to represent a point in 3D space in projective geometry. Okay, and the equivalent representation of this point in Euclidean space in 3D. Okay, 3D Euclidean space would be, what you do is x by 1, y by 1, z by 1. So these both representations, these represent the same point but in two different space over here, right? And we use two different coordinate notations for this. Okay, one is the homogeneous coordinate for the case of projective transformation, and we use non-homogeneous representation in the case of Euclidean space. Okay, so we just learned about these two coordinates over here. Now the next question is, so given this information, now how do we exactly represent a point at infinity, right? In the case of projective space. Okay, so what we do is, or how we define that is, a point at infinity is denoted by x comma y comma 0. Okay, so if you think of this now, we are talking about the 2D space. Okay, so in 2D space, this x comma y comma 0 is a homogeneous coordinate. Okay, in the projective 2D space, right? Now the equivalent of this one in Euclidean space would be what? How do we? So this is the projective space, and in 2D Euclidean space. Okay, can anyone tell me how do you or how do we write this? Yes, anyone? So if you look at this particular example, what I had said earlier was that if you have a homogeneous representation over here, right? Now to get the corresponding non-homogeneous representation, what you do is you divide the corresponding coordinates or each of these coordinates with the last coordinate, right? So using that particular definition, okay, what would be the point that you get for x comma y comma 0, which is basically a homogeneous coordinate representation? What would be the equivalent non-homogeneous coordinate representation? Anyone? It is basically x by 0, y by 0, right? All that you're doing is dividing by 0. And what is x by 0, y by 0? What is it basically?
Infinity.
Exactly, it is infinity. So the point that I'm trying to say is that in 2D Euclidean space, you do not have a coordinate which can be defined by x by 0, y by 0, which is basically infinity, right? But because you have this inclusion of a third coordinate in the case of projective space, okay, this x comma y comma 0 can be used to represent or to denote infinity. Okay, so whenever you deal with points at infinity, you use this particular notation, okay, or this particular homogeneous coordinate notation is used whenever you want to represent sorry, whenever you want to represent those particular points at infinity. Okay, so just remember, okay, I'll just sum up once again about what we were discussing so far. In projective space, right, and Euclidean space, we'll just look at the difference. So in the case of Euclidean space, we do not have a way of representing or denoting infinity, right, in terms of xy location. There is no system to represent a location of a particular point infinity. It is just a concept that we assume that parallel lines meet at infinity, that's all, but you do not have a particular point infinity or a definition of where exactly infinity is located, right? Now in projective space, what we do is we do define a particular location for point at infinity, okay, and we use the homogeneous coordinate representation to denote that particular location, okay. So that is where this the importance of homogeneous and non-homogeneous coordinate systems is important, right? So non-homogeneous coordinate system is something which you are familiar with, where any points can be represented by just x comma y. It can be x1 comma y1, x2 comma y2, etc. So those points which you represent using the non-homogeneous coordinate, okay, can be converted into the homogeneous coordinate by adding a third coordinate, okay. So this third coordinate which we are adding, okay, in the case of homogeneous coordinate, it is not a third what to say, it doesn't mean that it is a 3D space. Now this one, it is still in 2D space. In 2D space we need three different components or coordinates in order to represent a particular point, right? When it's to homogeneous coordinate system, right? And in the case of 3D, what we see is that we'll have four different coordinates in this case. Okay, so what we do is whatever be the space that you're dealing with, be it 2D space, 3D space, or so, or 4D space, or any space, you just add an additional component or coordinate to the non-homogeneous coordinate system in order to represent it in the projective space. So by doing that, what we are able to do, or how it exactly helps, is by giving a notation of 0 for that additional coordinate that you have defined in the homogeneous coordinate system. Okay, we are able to define or define a particular location for infinity. So now on, when you see, or when you're working with points at infinity, you can easily represent it this way. Okay, so that is one advantage of using the homogeneous coordinates, or basically using projective space or projective geometry when it comes to computer vision. Okay, we'll see in later classes how exactly it is used in different algorithms. But now just try to understand what is the basic difference between projective space and Euclidean space. Do you have any doubts so far?
No, no, ma'am.
Okay. Okay, now, so what we were speaking about was in 2D space, okay, we said that if you're talking about infinity, two lines meeting, so let's say you have a particular uh, image, right? And you have two parallel lines there, and it meets at a point in infinity, is what we have defined, right? So in 2D space, when you're talking about 2D space, when you say meeting at infinity, what we specify is, or what we assume is, a particular point, a point at infinity, right? But when it comes to 3D space, when you're talking about infinity, okay, so I'm not going to draw it. Basically what you have is a line at infinity. Okay, so it's no longer a point at infinity as in a 2D. When it comes to 3D, right, this point become a line, right? So if you want to visualize this, you can think of it as when you have two lines, right? If you imagine these two lines to be meeting at a point at infinity, that is as if let's say you're drawing two lines in a graph, and then you're trying to meet these two lines. That is basically in the 2D space. Okay, but when you have a 3D space, you have an additional component over there, right? You have an additional view over there, on an additional plane over there, right? So because of that, now when you're representing infinity, that would be a line at infinity. When it comes to 3D space, it's no longer a point, but a line at infinity when it comes to 3D space. Okay, just remember that point. Okay, just have a look at this particular figure, right? Now, this figure would help you to understand more about what exactly the point of, at infinity, or the line at infinity, exactly means. So let's say this is a long road, okay, that goes straight, and it keeps on going very, very, very far away, right? And you do not have any objects or obstacles along the road, or anything. So if you are let's say taking a picture of this particular road, right, this is how the picture would look like, where you see that, so basically in this road, these are actually parallel lines over here, right? These are parallel lines if you're looking at the actual scene over there, right? But if it is a long road which keeps on going, when you're taking a picture this way, okay, what happens is that you'll get a view which looks somewhat like this, wherein these parallel lines, right, tend to meet at a point. So this is just to trying to make you understand what is the concept of point and line at infinity. So this assumes to originate from a particular point, right? And we assume that this particular point that you have here, where the parallel lines meet, is what you can call as a point at infinity, right? Now, if you're looking at it in a 3D space, okay, or an actual view, right? So in 3D space, you can say that this particular horizon that we see over here, right, that is the line that can have many such points at infinity, right? So that is now defined as the infinity when it comes to 3D space, basically the horizon that you see over there. Okay, so just this is just for a visualization purpose to understand how exactly infinity is defined in terms of point at infinity and line at infinity in 2D and 3D space. So we'll also look at some representations of that later on. Okay. Coming back to Euclidean geometry, now we'll see what you mean by homogeneity. We discussed that in Euclidean space, you have the transformations, or the Euclidean transformations are basically the translation operation and the rotation operation. Okay, so if I'm assuming translation or rotation operation, so let's say I have a 3D space like this, okay, and let's say this is the object that I have, okay, and if the object is being rotated like this, right, I can say, so if I'm also rotating these axes over here, okay, just trying to draw this way, okay. So instead of saying that an object, okay, is rotating, what I can say is, or how I can denote it is that I can just shift my origin or my reference frame here, okay, to represent that particular rotation. Okay, so now for example, now my drawing is not right. This, if this object is a little bit more down, let's assume, okay, so in that case, if I'm rotating both, let's say the object as well as the axis, here also the object as well as the axis, if I'm rotating, you can say that both of the the coordinates that you get would be the same, right? Now let me take another situation where I have the object like this, right? And then I'm rotating the axis, let's say somewhat like this, okay, with respect to this image. If I take, okay, by rotating or by performing transformations on the reference system, when I'm changing the reference system from this to this, okay, this particular location or the points at which these particular corners or lines are represented change, okay, but actually the object that you have over here is the same, right? So you have an object over here, right, and it is the same object that I'm having over here, okay, but if I'm changing this reference system from this one, okay, if I'm changing the coordinates or the origin, okay, in some way, if I'm rotating it or translating it, what happens is that the location of these particular points, the denotation of the locations of these change. Like for example, a point at this particular location, let's say this corner, if it is x1, y1 in the case of, okay, so this is a 3D, so I'll have z1 also. Okay, if I'm representing this particular point using these three coordinates over here, maybe if I'm changing the reference system, the same point over here may be represented by x2, sorry, may be represented by x2, y2 and z2, right? But even if these values change from x1 to x2, y1 to y2, z1 to z2, if you look at these two objects, it still remains the same, right? So what I'm saying is that if you're looking at different points, okay, you can assume that this point as well as this point is the same, right? Provided you're just doing some transformation on the reference axis alone. Okay, so by changing the reference axis, the same point can be represented or will have different values of x, y, and z coordinates. Okay, so which means that, or what you can say is that all these points are homogeneous. Okay, homogeneous in the space, or the whole space is homogeneous in the sense every point, right, can be represented by some value of x, y, and z if we are just assuming that only the axis or the reference point, or by simply by changing the reference system or reference frame which is being used. Okay, you can represent the same point in multiple or different values of x, y, and z. So that means there is no particular distinguished point as such in the case of Euclidean geometry. Now that is an important point. Okay, there is no distinguished point. You have a particular point which can be represented by different values of x, y, and z, only depending on the reference system that you are using, or the reference frame, or the origin, the location of the origin that you are using. Okay, so therefore you can say that the whole space is homogeneous. But when it comes to projective geometry, okay, this is not true, right? In the case of projective geometry, we'll see that you cannot say that all points are homogeneous. We'll come to that. Now, just an explanation of what exactly translation, rotation, and scaling. So scaling is for affine, okay? This is for affine, which we'll see later. Now, translation and rotation. Can you tell me what kind of transformation it is? Anyone? Yes? I didn't hear you. Can you repeat? Okay, translation and rotation, they are basically part of the, or they are the Euclidean transformation, right? And we saw, or we already discussed earlier that you have the Euclidean space, right? Along with Euclidean transformation, if you're adding one more transformation, you get the affine transformation. Along with that, when you're adding one more transformation, you get the projective space over here, right? So basically, translation and rotation, okay, they belong to the Euclidean transformation, which also is valid, okay, or which is also allowed in affine space as well as projective space. Just remember that point over here, okay. So translation basically means you're just moving the object, you're just translating it, the location of the object changes, or from now on we are not going to say location of the object changes, we can say that the reference frame of the if even if you are changing the reference frame this way, right, you still have the basic shape, the lengths, as well as the angles preserved when it comes to translation. Now, the rotation, in case of rotation, right, it is just rotating a particular object. Okay, it can be assumed as rotating a particular object, right, at a particular angle, let's say theta in this case, right. So here also the basic properties, that is the shape, the angles, the lengths, etc., they're preserved, right. So these are basically the Euclidean transformations, right. Now this affine or scaling, what that means is, now scaling is just one example where you can assume it as just this is an example of this particular shape being shrinked, okay, or it is being scaled down, right, to lesser lengths, let's say. So we'll come to scaling or linear stretching later. Okay, so coming to homogeneity once again. So we saw that in Euclidean space, right, we have all the points, right, can be represented by just a shift of the reference points, and so we can say that all the points are in a homogeneous space, right, or all the points, there are no distinct points as such, right. Now, in affine transformation, as we discussed earlier, apart from Euclidean transformation of translation and rotation, okay, it also the other transformation that it takes is the linear stretching operation or the scaling, right? So, in affine transformation, as well as in Euclidean transformation, we see that the points at infinity remains at infinity. Okay, and the points, okay, some properties of the affine transformation are also preserved. We'll see in a tabular way how it is preserved also. Okay, and in projective geometry, right? In the case of projective geometry, we see that the points at infinity, they are not preserved. Okay, in the sense, if I'm assuming, let's say I have a value x comma y comma 0, right? That is a point at infinity. So if after applying a projective transformation, okay, it need not remain as a point at infinity. After applying transformation, you may get a projective transformation. This may change to some other point, let's say x1, y1, w1, right? So points at infinity are not preserved in the case of projective transformation. But in the case of both Euclidean as well as affine transformation, if I have a point at infinity, xy0, if I apply either Euclidean or the affine transformation, it still remains point at infinity, right? So I have some other notation, okay, but still it remains as point at infinity. So that is again one point which you have to remember later on. Okay, so just discussing some properties. Okay, so let's say here x, okay, this is a point which is represented by the homogeneous coordinate, right? So you have the representation as if it is in 2D space, you have x, y, and let's say 1. Okay, it's some representation. Now, by applying a projective transformation, right, I can say I get a new point x dash, and the new coordinates may be some other values over here. Let's say x1, y1, 1 here, like just an example. Okay, so projective transformation, uh, here one point you have to remember is that in the case of projective transformation, right, all the points, they are not the same, okay, or they are not assumed in a homogeneous space. We give a special consideration to the points at infinity when it comes to a projective transformation. Okay, now so when we were saying that in computer vision we deal with projective space of projective transformation, right? So why do we go with that, or why do we go with projective transformation? One reason is because you have a representation of infinity. Basically, you can represent it with x comma y comma 0, right? And another reason why you're going for that is because here it is in real 3D world. That is the kind of view also that we see. Like for example, in the first slide we saw that when you're trying to capture an image, right? If it's exactly perpendicular, if the camera viewpoint is exactly perpendicular to the surface of the particular plane or the object that we are trying to capture, then we get a perfect, preserved the shape as well as the length. Mainly the length and the angles would be preserved, okay, when we are capturing the image. But when it comes to changing the viewpoint, what happens is these are not preserved, right? So most of the time when you capture those images, okay, or the images that we are dealing with, it's basically a projective view that we are dealing with, right? So this projective space or projective geometry would be the most convenient way of trying to deal with real 3D world problems, okay, or developing algorithms that deals with these real or practical problems, okay. And another point is that one more point about the projective geometry is that it is what it is not homogeneous, or in the sense all points are not treated equal, and we give a special consideration for points at infinity or lines at infinity, okay, when we are working with practical problems. So just remember these points. Okay, now coming to the difference between the Euclidean, the affine, projective transformations. So as I said, in Euclidean transformation, you can have translation, you can have rotations, right? In the case of affine transformation, right, you can have shearing. And in case of projective transformation, you have a set of projective transformations where None of the angles, shapes, lengths, orientations, none of these are preserved. Okay, the only thing which is preserved is the straight lines. So just to give you an idea here, in projective space, the only thing which is preserved is the straight lines. That is, straight lines remain straight lines after projective transformations. When you're doing affine transformations, what you see is parallelism is preserved. Okay, the angles and lengths may not be preserved, but parallelism is preserved. Like for example, if the initial picture that you had, okay, if it is a square, after a shearing process, you may get something like this, right? So the parallel lines still remain parallel lines, but here the angle, right, it does not remain or it is not preserved. Okay, then similarity we are not looking. We'll look at Euclidean space, right? So in the case of Euclidean space, what we see is that the orientation as well as the lengths both are preserved in the case of Euclidean transformations. So let's say you have, if you want to do some kind of measurement of any lengths of any objects or any angle between two lines, etc. Any measurements with respect to orientations or lengths can be done correctly only in Euclidean space. Okay, but when it comes to projective space, that is the most convenient way for us to deal with the actual images or the real world images, right? So many a times what we do is in computer vision algorithms, we may have to switch in from the projective space to Euclidean space and Euclidean space to projective space, vice versa. Right? That is, if it involves any kind of measurements, we cannot measure in the projective space because none of the lengths or the orientations or the angles are preserved or the shape is not preserved over here, right? So the measurements won't be correct, so we cannot do any measurements over here. What we do is we go to the Euclidean space for any such measurements, right? So therefore we also need to know how we can uh, convert or how we can transfer from the projective space to the Euclidean space and vice versa. Okay, we'll see that in the next slide. Okay, so this is again another representation. So let's say this is the input image. I have the input image as a square, right? So in the Euclidean space, I can have a translation or a rotation. So this is an example of a rotation. And we see that the angles are preserved, the distances are preserved, the area is preserved. So these are the properties that are preserved within the Euclidean space or Euclidean geometry. So what it means by preserving these properties is even after applying the Euclidean transformations, the transformations that are supported or that are allowed by the Euclidean space, these properties are still preserved, right? So that is the example for a Euclidean geometry or Euclidean transformation. Now, an example of affine is where you're doing a shearing, right? So when you're doing a shearing process over here, what happens is, let's say you're getting an image this way, right? So the only thing which is the only property which is preserved in this case is parallelism, right? And as we've already seen in the case of projective space, okay, parallelism also is not preserved, right? The only thing that you have is basically the straightness of the lines, okay, and the fact that the lines will always meet at a point. So even if you have a point at infinity, you have a representation for such points at infinity in projective space. Okay, now coming to affine geometry. So in affine geometry, we saw that if you're adding or if there is an additional along with translation and rotation, if there is a scaling factor, right? So that would take us from the Euclidean geometry to the affine geometry, okay? And we'll see how we can move from affine to Euclidean or vice versa also later, okay? Now, as I said earlier, right, we may have to move from certain spaces like the Euclidean space to the projective space or the projective space to Euclidean space and so on, right? In Euclidean space, if you have to take some measurements, right? Now, for moving from Euclidean space to projective space, we have already seen that what we do is you have an or what we have an additional component or a coordinate, a third coordinate. In the case of 2D space, we add a third coordinate to the Euclidean system to get the projective transformation of the projective space, right? Now, how do we convert back from projective to Euclidean? We'll see that. Okay. So for Euclidean to projective, all that we do is we add a particular third coordinate, right? And we convert from Euclidean to projective space. Or in terms of theory, we can say that we have an additional representation of the infinity when it comes to projective space. Now, how do we move back if we have a projective space, right, or an object in a projective space? How do we come back to the Euclidean space, or how do we represent the same thing in Euclidean space? So for this, what we do is we do not directly come back, right? We first convert from the projective space to affine space, and then from affine space to Euclidean space. Okay. So whether it is 2D or 3D, what we do is from projective space, okay, we transfer, we move from the projective space to affine space, and then from affine space we will go to the Euclidean space. So how do we know we are in projective space, or how do we know we are in affine or Euclidean space? That would depend upon what properties are being preserved in each of these spaces. So we know that in projective space, there is no concept of parallelism, right? But if we can identify, or if we can represent two lines, infinite or parallel lines in projective space that we are dealing with, then that means that particular object, or that particular points that we are dealing with, or the lines that we are dealing with, it is or the object, it is no longer in projective space, but it is in affine space, right? And so and from affine space also, once we know what is the line at infinity, right, from there also you can go to Euclidean. So we'll see that how it goes one by one. Now before that, if there is any doubts, I'll take that. Okay, yes, yes, tell me.
Yes,
Is there a
yes.
doubt?
No, no. No doubts.
Okay. Are you able to follow? Did you understand what is Euclidean geometry, affine geometry, and projective geometry? Are you able to follow what you mean by preserving the properties of the image? What do you mean by preserving the shape, the length, the angle of the objects?
Yes, ma'am.
Okay, okay, okay. Then I'll move on. Fine. So, in the case of affine geometry, as we said, if we are able to identify two lines, okay, in the projective space, then we can say that the concept of parallelism, since that has been identified, you can say that it's no longer in we are no longer in the projective space, and we move on to the affine space. Okay, so we will see that here. So what we do is we pick out some particular line, okay, and then we try to identify two parallel lines, or we try to identify. So how do we know that there is an existence of parallel lines? Because what we assume is that parallel lines would meet at infinity, or it would intersect at infinity, right? So if we are able to identify this particular infinity, or let's say the line at infinity, that is line at infinity in the sense the collection of all the points at infinity, or the line that passes through all the points of infinity, can be called as the line at infinity. So in if we are in the projective space, if we are able to identify this line at infinity, right, then that means there is a presence of parallel lines, and therefore we can say that it is, since the concept of parallelism is there, right, then we can say that it is no longer in projective space and we are moving on to affine space, right? So once this line of infinity has been identified, or we have found the distinguished line at infinity, then what we do is along this line we try to find out what is the point at infinity, right? So if we can identify a particular point at infinity, or what we are doing is we are trying to identify how exactly the what I say we can convert from affine to Euclidean, right? So from the line at infinity, if we are able to single out, or if we are able to find out one special feature of that line, right, then we can move from the affine to Euclidean geometry. So this is how we are trying to move. What I'm saying is, if I have a Euclidean geometry space, and by applying the concept of infinity, I can directly go to projective space. But when I'm going back from projective to Euclidean, what I'm doing is, first I go to the affine space, and then I move on to the Euclidean space, right? So from the projective space to the affine space, how I move is by identifying the line at infinity, right? And from the affine space, how I move on to the Euclidean space is by finding the points at infinity. So we'll see that in detail. This is something which we've already seen, what it means by the point at infinity and line at infinity. Okay, we'll move on to this now. Okay, so here when you are applying, when you are saying that you are singling out a special feature, okay, from the affine space, okay, that particular feature can be called as the absolute conic. So just note down this particular name or term, because we'll be dealing with that later, okay. So absolute conic, it's a very important concept when it comes to reconstruction, okay, and it is something that you will be studying about when we are moving from the affine space to the Euclidean space. Now, in affine space, we know that there is linear shifting or linear stretching, right? So if I look at circles, in the case of affine space, if I look at circles, right? So there is no concept of circles as such in affine geometry, because when you're talking about affine transformation, what it means is the transformations which when applied in the affine space should not, or should preserve all the basic properties of that particular space, right? Now, in affine transformation, one of the transformation of affine space or affine geometry is the shearing process, right? So when a circle, if you're taking a particular circle, right? When you have a circle, and when if you are applying some kind of a shearing process, what happens is that it may change the, so you have a diameter over here, it might change the length over here, so it might become an ellipse in this way, right? So this shearing process, which is allowed in the affine transformation, would change the circle to an ellipse, right? So we say that there is no specific representation of circles or definition for circles when it comes to affine transformation. So circles are just another what to say, another kind of ellipse when it comes to affine transformation. There is nothing separately as we call as circles and ellipses in the case of affine transformation. If you're dealing with Euclidean transformation or Euclidean geometry, circles are different, right? Ellipses are different, right? But in the case of affine transformation or affine geometry, right, the circles and ellipse, they are basically, there is no distinction between that, because you can say that circle is just another ellipse which has been formed from some kind of affine transformation from another ellipse. Okay, it can be thought of that way in the case of affine transformation. So just remember that point. Now, if you look at an ellipse, right? If you look at the equation of an ellipse, basically it's, what do you have? X squared by a square plus y square by b squared is equal to 1, right? So that is a second degree equation, right? Now, if you try to solve for the points of intersection of two ellipses, right? What we see is there would be 4 points of intersection. You have this point over here, this point over here you have a point, and here you have a point, right? So there'll be 4 points of intersection when it comes to two ellipses being intersected upon each other, right? Now, what about circles? If we try to assume how many points of intersection are there in circles. So if I look at the equation of a circle, basically the equation can be represented as x square plus y square is equal to r square, right? And because it's a second degree equation, again, you can assume that there would be 4 points, right? But if you look at circle, basically this is a circle you have here and another circle that you have here. So it has only 2 points of intersection, right? So remember that when it comes to circles, right, there are only 2 points of intersection. And the concept of circle, it is only in Euclidean geometry. So in Euclidean geometry, when you're dealing with circles, there are only 2 points of intersection for that. Except for there are cases where there could be just 1 point or multiple points. We are not considering that. Like for example, if you have two circles like this, you will have a point of intersection, or if you have one circle over the other, we are not considering these cases, right? But if you just take at two circles which are kind of a little partially overlapped, right, you have 2 points of intersection, right? But in the case of a fine geometry, since you do not have a specific definition for circles, right, circle is also just another ellipse, right? And being ellipse here, you expect 4 points of intersection when it comes to ellipses. Okay, so this is what I was talking about in terms of the circles, the points of intersection for the circles. Now, so for a circle, if you try to represent a circle in terms of homogeneous coordinates, that is, now for homogeneous coordinates, we know that there are three coordinates to represent a particular point, right? So the three coordinates can be x, y, and w. So the corresponding equation of a circle in homogeneous coordinate can be written as x minus aw whole square plus y minus bw whole square is equal to r square w square. Okay, so this is the equation of a circle in homogeneous coordinate, right? And the center of the circle in the homogeneous coordinate system can be represented as a comma b comma 1, right? So here what you have to remember is that it's just that the representation changes over here, okay? But basically the basic object that we are dealing with, right, that is the same, right? Now, if you have to convert this particular homogeneous or this particular equation represented in the homogeneous coordinates, okay, if you want to convert that to the non-homogeneous coordinate, what do we do? Can anyone tell me what we do for converting a point in a homogeneous coordinate system to non-homogeneous coordinate system? What do we do? Yes, anyone? Okay, can anyone tell me what is a homogeneous coordinate system, or what are homogeneous coordinates? Okay, I'll just repeat the question in one more time. Can anyone tell me what do you mean by homogeneous coordinates?
We could use such coordinates for affine and projective transformations.
Okay, good. How is it different from non-homogeneous coordinate?
Non-homogeneous, it's like It's a simple. You. Uh,
A point, how do you represent a point in non-homogeneous coordinate?
exact x coordinate, y coordinate, and z. So.
Yes, yes, exactly. So the corresponding homogeneous coordinate, how would it look like? Just an example. You will have one more additional coordinate over there, right? So if you're looking at in this particular example over here, I have x comma y comma w. Okay, so this w is the third additional component which I'm or additional coordinate that I'm adding to represent the same point x comma so in this case it would be yeah, that was my question, so I want to answer that. So this is a representation in the homogeneous coordinate, right? Now my question was for this particular representation, if I want to and we saw that this is the corresponding equation for the circle, right? Now if I want to represent this point, okay, or this coordinate over here x y w, to convert that to non-homogeneous coordinate, what should I do? So non-homogeneous coordinate will have just two coordinates, right? Or two variables. Let's call it variables here. So how do I calculate that from here?
So would it be x by w and y by
Yes,
w?
exactly, exactly. Very good, very good. So what we do is basically to convert this to the non-homogeneous coordinate, right? So which will have only two coordinates when it comes to 2D space. What I do is I should divide by the third coordinate. So I have x by w, y by w. Okay, so the same concept goes over here also. So let's say I have a point which is represented by x comma y comma 0 in the homogeneous coordinate system. Okay, can anyone tell me what would be the equivalent non-homogeneous coordinate?
Is it infinity?
Yes, exactly. It is infinity because when you're dividing by the third coordinate, you have x by 0, y by 0, which is nothing but infinity. So here, this representation, now x and y can have any values, but if the third coordinate in the homogeneous coordinate system, if it is a 0, then that means that this is a point at infinity. And you can have several points at infinity, and the line which joins all these points at infinity can be called as the line at infinity. Okay, and here this is a homogeneous representation. If you want to convert that to the non-homogeneous, all that you do is divide by the third coordinate. Okay, now if I have a 3D space, let's say I have a 3D space and I have a representation, the homogeneous representation, let's say I have it as x comma y comma z comma w. Okay, and to the what would be the corresponding non-homogeneous representation in 3D space? Can anyone tell me that? So in non-homogeneous, the 3D space representation, how many coordinates will I have? And what would be the values there?
X by W, Y by W, and Z by W.
Very good, very good. So x by w, y by w, and z by w would be the coordinates in the non-homogeneous coordinates. Okay. Now, what we see is now this is the representation for the non-homogeneous coordinate system, right? So if I substitute the values of x and y over here by x by w, y by w, what I basically get would be the equation of the circle in the non-homogeneous coordinate. Okay, and as I said, non-homogeneous coordinate, right, non-homogeneous coordinate can be used to represent the Euclidean space. So basically if you have x comma y, that can be used to represent a point in Euclidean space, right? And homogeneous the coordinate system where you have x comma y comma, instead of w I just take it as 1, just to make you understand that this is not a 3D point, it's still in 2D space, right? So the corresponding point, okay, in Euclidean space, okay, that would be having just x comma Why in this case, right? Now, this homogeneous, okay, what I was saying was here, this homogeneous coordinate would represent the projective space or the projective transformation in this case, right? And here in projective space, there is a representation for infinity, and that representation is just by giving a value 0 over here. Okay, and okay, let me ask another question. In projective space, can anyone tell me in projective space, does it preserve parallelism? Yes or no answer. Does it preserve parallelism?
No.
Okay, good, very good. So in projective space, parallelism is not preserved, right? Can anyone tell me then what is preserved? What property of a line is preserved in projective space?
Straightness and intersections.
Yes, very good, very good. Okay, good. Now, fine. For Euclidean space, can anyone tell me in Euclidean space what are the properties which are the properties of an object which are preserved in Euclidean space? That means properties which are preserved means even if I apply Euclidean transformations to that object, that transformed object which I get will still have so and so properties preserved in that. It still remains the same. So what are those properties? Can anyone tell me that? In Euclidean space, the properties which are preserved.
Shape.
Yes, shape. So shape means, yeah, basically, so shape, or more specifically, it would be the angles, the lengths, okay, all these would be preserved in the case of Euclidean space. And can anyone tell me a few transformations which are allowed in the Euclidean space, or which are invariant? That is the exact name for that. Which are invariant in the Euclidean space, or which are allowed in the Euclidean space. Certain transformations that are allowed in Euclidean space, or which the Euclidean space supports.
Rotation.
I can't hear you. Can you
Uh,
repeat?
could it be rotation around one point? Maybe so.
Yes. Yes, rotation. Yes, very good. Any other operation?
Then
Translation.
translation.
Translation. Okay, okay, very good. Very good. Okay. Mm, okay, fine. So it's already 5:30 now. So we'll continue with the affine geometry and how exactly we move from projective geometry to affine geometry and affine geometry to Euclidean geometry in the next class. We'll continue from this slide. Okay. So meanwhile, if any of you have any doubts regarding this, what I'll do is I will upload the slides, and if you have any doubts regarding any of the concepts or any of the points which have been discussed in the class today, please get back to me. You can either email me or WhatsApp me, or you can send a chat in Teams. Okay, so please get back to me offline, and we'll continue in the next class. Okay, thank you.